and I will let you all take it from here. Let me know when you would like me to help you with anything to make another poll, and I can read chats from the Huba session as well and on Zoom. So thank you.
Sure. So starting. Okay, let me introduce myself. I'm Paul Takistov, professor, School Environmental Biological Sciences. My home department is Food Science, and I'm from Rutgers University. And with your permission, I'll start to share the screen. And let's talk about something good and interesting. We'll talk about the nanotechnology. And this short course actually is the part of the GARD Academy and several very good short courses which provide very good intro to the topics which are interesting for all of us. It's very difficult to teach and talk about nanotechnology just in 30 minutes, but we will try to cover some basic fundamental principles. So first of all, size does matter. And actually, the size determines the properties of material, which surprisingly we all learn in the school about colligative properties, which are size independent, but also it impacts the forces that dominates. And the forces, that's what we'll talk today, mostly in the fundamental part. Let's talk about the dimensions. We are on the planets with the length scales. We talk about 10 to 3, 10 to 5 meters. If we will go down a little bit, the everything which we can manipulate by hands and eyes, we can talk about 10 to minus 2, 10 to minus 3 meters, which is millimeter. Our hair, it's very natural length scale. It's about 50 microns. And all food structures, all biological cells, all biological components, they're ranging about 10 to minus 6 meters, so the micron range. The plant cells, it's about 30, 40 microns. Mammalian cells, 10 to 20 microns. Microbes, about 1 micron. And after that, we're jumping in the region of the submicron scales. With the viruses, level of the 100 nanometers. Macromolecules, we talk about 10 angstroms, and molecules are less than 1 angstrom, which is 1/10 of the nanometer. So formal definition of nanotechnology is something from 1 to 100 nanometers, which now it's expanded if materials are at least in dimension exhibit properties different from the bulk, they can be claimed as nanomaterials. So for many systems, we talk about 200, 300 nanometers characteristic size. So the sheet of the paper that we're taking notes during our classes and our meetings, it's about 100,000 nanometers thick. So why are we talking about nanotechnology? Why are we separated from other fields of the knowledge? Because if you can take a look, there is huge overlap between the colloidal science, interfacial science, material science, engineering. Because only recent development and understanding allow us to manipulate targetedly material at this scale, design new materials, and form new materials, new interfaces with the properties. Therefore, we can manipulate materials and chemical phenomena, properties and functions, which are scalable to the nanometer domain, which was impossible 20, 30 years ago. We can measure, control, and manipulate matter at such scale. And this unique domain actually is interface between discrete materials, between separate individual molecules, and continuous phase. And therefore, the manipulation of the materials at nanoscale will allow us to integrate along length scales and build up continuous materials with the different scales, with the different architecture. Different properties are not just limited to the surface to volume ratio. Of course, we know that heat, mass transfer, the all reaction, they are going through the interface. And if we scale down the material, we will see significant increase in the surface area, and therefore many processes will go differently. But also, this increased surface area might lead to the different chemistry and different surface properties, as we will see a little bit later. All natural materials and most of engineered materials, they are heterogeneous by nature. And therefore, we see the interplay between different elements on the surface, which will create unique properties that can be targetedly manipulated. So let's go back historically, how our fundamental understanding of the material came from. And actually, it started in 19th century, age of steam, when we need more power, more speed, and better machinery. Before we knew only ideal gas equation, at that time, actually, molecular theory of the matter was not commonly accepted in the scientific community. But with high pressure, with high power steam engine, the properties of the steam were different. And Johannes van der Waals, he assumed just historically that, just empirically, that there are different properties. The molecules are not points. And there are some interaction between molecules. And he proposed update to the ideal gas equation. It's so-called van der Waals equation. And actually, base of this equation is the presence of the some attractive forces between the molecules. It took almost 100 years of the joint efforts of scientists from physics, chemistry, and mathematics to understand the mechanism of empirically postulated van der Waals forces. Yes, there are attractive forces between molecules. In all materials, between all molecules, they consist from three major components, but there are several more. The chiasm interaction actually is the dipole-dipole interaction, and well-known hydrogen bonds is the actually particular case of the chiasm forces. Debye, who is the father of the modern theory of electrolytes, actually he developed the theory of the induced dipole interaction. So polar molecule can induce some dipole in non-polar molecule. And the most interesting finding was developed by the London in 1950s. It was possible only when the quantum chemistry was developed, that even non-polar molecules, through their stochastic movement, can develop some kind of dipole, and therefore they interact with each other. The most strongest dipole-dipole interaction chiasm forces, but except some polar solvents like water, usually these interactions are weak because of the small number of molecules, polar molecules present in the system. The biforces are more significant, but the weakest by the magnitude, but largest in the amount of molecules involved, the London dispersion forces are the most common, and they contribute about 60% to all intermolecular forces. I'd like to note that all these intermolecular forces, they have common name as van der Waals forces. They exist in all materials and they're always attractive. This is why we have liquids as liquids, solids as solids, just because of van der Waals forces. These molecular forces are short-range forces. They decaying in power -6, accordingly to the intermolecular distance. And they should decay very, very fast. It took another 30, 40 years when Hamaker calculated the van der Waals interaction forces. And he came up with extremely interesting conclusion. He used so-called Dirac approximation, calculated all pair interactions in the material, and found that the forces decaying much slower. In between molecules, forces decay 1/r in power 6, that r is the distance. But between surfaces and particles, these forces decay as power 2, which means that van der Waals forces, when we talk about the continuous material, when we talk about particles and surfaces, they are long-range forces, and they can extend their action up to tens of nanometers. Therefore, the larger material, the more van der Waals forces. How about 2 rocks or 2 stones? Yes, there are strong van der Waals forces there too, but at that scale, the gravity forces and momentum transfer will dominate. But in the domain of the nanoscale, colloidal domain, when we talk about between 1 and hundreds nanometers, van der Waals forces will dominate. When we have surfaces in gas or so, there is no associated charges. All natural surfaces, all engineered surfaces, except maybe some high molecular weight polymer surfaces, they have some uncompensated charges due to dislocation, chemical heterogeneity, irregularity of the surface, many reasons. And when we have symmetric molecules around like gas, nothing happens. So we have only van der Waals forces acting. But when we put such surfaces into contact with the liquids, like electrolytes, we have positive and negative charges, which will result in the redistribution of the charges next to the surface, and this structure called electrical double layer. The counter ions, because we know the liquids are conductors of the second kind, when electrical charges carried by the ions, by charged particles, they will go to the surfaces, and the ions of the opposite charge will push away. In the bulk, we have the same amount of the positive and negative charges. At the surface, we have breakdown of the electron neutrality. And therefore, if we apply electric field or we introduce movement, we'll have the redistribution of charges, and we have whole spectrum of phenomena that call electrokinetic phenomena. electrophoresis, electroosmosis, Donan potential, streaming potential, and many, many others. So now we know the major players. We have electrostatic repulsion forces because of the charged surfaces, and we have van der Waals attractive forces. In the mid of 20th century, four scientists, Dirac and Landau from Soviet Union, and Verwey Overbeck from the US, they independently published two papers just a few months apart when they proposed the major contribution to the what we call foundation of the nanotechnology, the force balance approach. Based on the strong physical understanding, they make assumption which experimentally confirmed fully that attractive and repulsive forces are independent, and therefore the total energy of the material interaction can be represented as the sum of these two independent forces. So attractive forces, van der Waals forces, repulsive forces are electrostatic forces, and therefore it appears that this force balance describe very, very complex behavior. When energy is negative, there is attraction, energy positive is repulsion. And as you can see here, you see the calculation of the van der Waals forces. You see it's very, very long range forces, more than 30 nanometers. And on the top is decaying electrostatic forces, which decay 1 power exponential. And the resulting sum, we see some negative region, which called primary energy, a secondary energy, which weak interaction, we create flocculus, and in the solution, we will have very weak aggregates, and actually apply a little bit mechanical force, you can disaggregate. After that, we have region when we have the electrostatically stabilized system, when the repulsion dominates over the van der Waals attraction. But if we push particles close, what does it mean put close? The distance means concentration. The distance between particles proportional to the cubic root of the concentration particle per volume. If we put more particles, which means that you see via primary energy minimum, particles will aggregate, coagulate, and precipitate. So with this theory, if we know properties of the material, we can predict the behavior. So now we know that the major principle is the force balance. The major principle is understanding of the surface, bulk, and interfacial forces. This is not all. At this scale, at nanoscale, there are several fundamentals phenomena which will determine the properties of material. First of all, is the so-called Kelvin effect, who investigated evaporation of the and boiling of the liquid in capillaries and found that the solubility will increase. This is actually all nanotechnology application in the drug delivery. It's to control the solubility, and everything is based on the Kelvin effect. Depression of the melting point, the major thermophysical properties in the phase transition based on the Gibbs-Thomson theory. If you don't know, Gibbs was the first scientist who was awarded PhD in engineering in the US. It was 1863. Accordingly to the Stokes and Stein principle, the diffusion rate will increase, but actually at nanoscale, we see even anomalous diffusion, which not covered by the Einstein law. And also experimental observed, but theoretically not described, so-called rebinder effect, increase of the amorphous fraction during the interaction of the materials in our skin. So we have forces, we understand how it works. And this knowledge will allow us to, using such forces, manipulate with the material. Just look at this. We can make small nanoparticles. How we can make? We can apply external forces like shear forces, like a different type of the device, like colloidal mill, ultrasound, name it, and break down the material working against the Gibbs energy. Okay? We can make the composite materials with different types of fillers. We can put droplets, we can put polymers, we can put in other particles. We can manipulate with the surface properties, so-called layer by layer deposition, or decorate surface with particles and fibers. We can do it with different phases or even assembly of the particle. How about surface? If we have nano-patterned surface, which can be done chemically, which can be done with self-organization, like famous nanoporous aluminum or nanoporous silicon, and we can use small particles and small cavities on the surface as the new reactors, new material to build new properties of the interface. We can deposit catalyst and control chemical reaction. We can integrate, deposit and create new, optically active elements. We can integrate biochemical elements to create new biorecognition sensing devices. And you see, manipulating at different scales, everything requires only one thing: understanding of the forces at the interface. Now I'll go just few examples because my time is limited. So making nanoparticles. One of the easiest way is to use the phase transition. For example, solid lipid nanoparticles, they are widely used in the drug delivery applications and also used to deliver nutraceuticals in the or cosmeceuticals in the food or personal care industry, actually making emulsion at high temperature and control the phase transition during the cooling. And actually manipulating with the material, you can control the internal structure of these crystals and therefore control the rate of the release. Another interesting application is used for the drug delivery and also used for the structured vegetable oil. It's called molecular gel. We all like to be healthy, and therefore we'd like to get rid of the animal fats going to the plant-based oils, but they are liquid at room temperature. We don't want chemically modify them, therefore we can introduce the material which is health friendly, but also create network of nano and micro scale crystals within the material, and therefore we can get gels which will be good for our health. Using interfacial science, we can control the self-assembly of the polymers. For example, this is a zinc, and depending on the conditions for Marangoni flow, which is the flow due to gradient of the surface tension, which is surface tension. It's again uncompensated van der Waals forces at the curved interface, and we can get everything from the continuous film, which used in the package, to the nanoparticles, which use in the drug delivery. We can use the high shear induced self-assembly of the material, changing the phase composition, for example, through the evaporation, and we can encapsulate materials, which again can be used for the delivery or building the new system. This is by inspired word formulation. When we use the microbial cellulose, the nanoscale cellulose fibers that produced by bacteria to use for the coating and control release of the target substance. And depending on the formulation, we can use these nanofibers at different scales. This is example of the drug delivery when we can make the suspension, emulsion, and composite film. And you can see that, for example, drug particles on the right picture, if they're at nanoscale, they will absorb it very, very fast. 70% of the drugs are not water soluble. And this is the big problem, how to deliver them to the human body without chemical modification. This is an example how we can use nanoporous substrate, specifically aluminum, and electrokinetic phenomenon, electrophoresis, how we can put nanoparticles inside the pores. The size of the pores is about 10 nanometers. And actually, we create photonically active structure that can be used for the optical biosensors. Nanoparticles. On the left side, you can see the commercial size of the particles, and with the developed technology using the ultrasound and some additional regimes, we can get the nanoparticles. And on the right side, you can see interaction of such particles with the bacteria, pathogenic bacteria. And on the plot, you can see we can completely suppress growth of the bacteria, so making our foods, our drugs much more safe. The photodynamic inactivation, just light and particles will be activated and pathogenic bacteria will be completely destroyed. Just few examples of what we can do, but this is the example of the devices that can be built based on the nanostructured nanoscale material. So the devices that can combine sensors and release of antimicrobial agent, using maybe one of the most common instrument when we talk about nanotechnology, we definitely think about atomic force microscope. We can directly monitor changes of the surface when we see a immune reaction, antibody antigen reaction, which is common for most of our sensors. We can see, we can monitor, and we can quantify what happens at the level of nanoscale. And this based nanoparticle-based sensors, they can be used just part of the intelligent packaging system with the color indication when our food is fresh or not, or was thermally abused. And the last example, the small patch with the gold nanoparticles will allow direct detection of the contaminants of the milk through the package with the Raman probe material. So I try to be just in time, I believe it. So it's not just course in nanotechnology. What I try to show that there is no magic. It depends the success in nanoscale materials in nano application, not based on the availability of the expensive instrumentation, but more on understanding of the forces that are critical at nanoscale domain at interfaces. So the nanotechnology as a field formally exists, I believe, for 22 years now. But the directions are still the same. New nanomaterials. With new application, with new demands, we need more and more materials that are precisely designed at nanoscale. We talk about bottom-up approach in the designing of the materials, not just top-down. We'd like to be healthy. We need better delivery systems. We need better diagnostics. We need more tools to design and control material properties. And of course, as we all colleagues in the field of biodetection, we need nanosensors, because everything that we can detect, it's everything at the tiny, tiny interface. And of course, we're living in the transparent world with the global economy, with the global transport network, and therefore we need the identity of our products and identity of everything around. Okay, thank you very much. And if you have questions, I will be happy to address. Okay. Okay, if you have any questions, I will be happy to answer. My email is available, and now I'm passing. Yes. Okay. Thank you. So, Olga, the class is.
Thank you so much, Paul. I think it's I don't know if I can mute or not.
Oh, you're unmuted, but do you want me to tell you all the questions at the end of this presentation, at the end of the
I think so. This will be a good
Okay.
idea.
Okay.
Yeah. So I'll go ahead and share. Can you see my screen in the presentation mode? Okay, good. So Paul already told you about the nanomaterials, right? And how the properties changes with size, and the amazing ability we have to control basically those properties at the nanoscale level and design new materials and basically, let me see if I can progress. Okay. Which result in many, many applications. And he already touched up on applications for biosensors, for medical applications and drug delivery. We have environmental applications. This is just example of basically applications of nanotechnology in agriculture. What I would like to really emphasize and a little bit switch gears from the ability to design and how to synthesize particles to also kind of raise concern that when we design the particles, we need to ensure that we are trying to make them as safe as possible, those nanomaterials. Why do we concern about that? Basically here, when we are producing the nanomaterials, right, or the nano-containing products, and when we use them during residential use, when we dispose them, eventually they go into wastewater. Into wastewater treatment plants, they partition to sludge, and sludge is applied to agricultural soils as biosolids. So after sludge is applied to biosolids, the particles are actually entering the soil systems and being taken by plants and eventually serve as food for the people. There is also incinerations of the materials in the landfill and hence emission in the water, in the air. And finally, we have runoff, right, of the soils, so the nanoparticles eventually enter the water systems. So this is kind of one health approach to estimating potential risk from the exposure to nanomaterials, which include estimating risk to humans exposure and to environmental exposure. And if, for example, when we are using nanomaterials for drug delivery, right, we are mainly kind of concerned with human exposure. However, when we, for example, using nanomaterials like as nanopesticides, and we are spraying them in the field, like the farmers spray in the field, then we have increase in occupational exposure, increase in release in sediment, water, soil, and obviously there is also food transfer through the food chains, and eventually it can reach also humans. There is also indirect effects directly on humans, such as if the nanomaterials interfere with plant yield, for example, then it's indirect effects, right, resulting on the plant growth. So what do we do? That's where nanotoxicology comes into play. And nanotoxicology is basically a study of the toxicity of nanomaterials in order to predict and evaluate the potential environmental and human health risk. So we start with screening at in vitro. So basically that's usually used for high through output screening or to actually understand maybe mechanistic interactions of nanoparticles with proteins or the cells. But that's used as initial tool. And then we need to continue with in vivo screening, where we're using whole organisms. In this case, the examples is with zebrafish hatchery. There are also other in vivo organisms before we get to, for example, mammalian screening. Mammalian screening would be too expensive. So before we get to screening in mammals, we can also use such organisms, such model nematodes, such as Cyanarhabditis elegans, which has very short life cycle. It's 3 days, and this is just different endpoints. Let me see if I can get laser pointer. Okay. And this is just different endpoints that can be estimated just using nematode. There is also a lot of conservation and biological pathways with mammals. So it is predictive tool for toxicity in mammalians too. So as Paul already mentioned about how properties changes with sizes, there are a lot of different properties that make those nanoparticles or nanomaterials unique, right? And hence enhance their basically ability to be used for different applications. However, those properties also affect eventually their bioavailability in the organism and overall have effect on the toxicity. So we have here a size, solubility, surface chemistry, shape, concentration of the particles, chemical composition. And sometimes it can be depend on size, right? So if you look at different size and the toxicity change with the size. Also, if you have different surface coating, toxicity can change with the surface coating. And it's not that simple. Often we have multiple factors that are playing a role. In this case would be size and coating both will play a role in predicting toxicity. Finally, we have prediction of biological effects from in vitro screening to in vivo. Are they really directly translatable, or we really need to be on caution side? So Chelsea, if you can put the poll. So the next poll, basically, which property do you think would be critical when assessing toxicity of unstable silver nanoparticles in aquatic media? I cannot see responses live. Oh, can you see responses?
No.
I just made it because I just found out about this poll, so people should be able to see it now.
Okay. Can you see the response? Because I don't see response on mine.
I see one response, dissolution. So if people would like to respond to this, please go on the Hoover app. The poll should be over there. And someone else put C, someone put A.
I see. So there is some confusion, right? A little bit. And actually, in a way, they would be correct that size shape would have effect too. But in the equation, I put unstable. Unstable meaning they're prone to dissolution. And yes, C would be really important for determining toxicity of silver. And with silver, basically, when silver nanoparticles enter environment, for example, aquatic environment, then they oxidize and silver ions are being released. And those silver ions determine toxicity of silver nanoparticles very frequently. And that's why Paul even was mentioning that a lot of times in, for example, drug delivery, one of the main purpose is to control dissolution. So the silver nanoparticles is very critical, the dissolution. And this will show basically, those graphs will show why. So if you looked at silver nanoparticle toxicity to different organisms, you can see, for example, that it is very toxic to Daphnia, right? This is Daphnia here. But if you look at that scale for silver salt, which is silver ions, then the nanoparticle ions, silver nitrate, would be much more toxic to Daphnia than the particles alone. So if the particles are being released, even at small concentrations, there still will be causing toxicity. So as I mentioned, the other properties are also important, size, shapes, and coating, especially for the particles that are stable, such as gold or silver. And this is study example of the study done with gold nanoparticles in mice. And they just looked at different sizes and different shape and different coatings and their bioaccumulations in different organs. And you can see that, for example, with size, as the size decreases, the accumulation changes. And if it starts with highest in lungs and liver, then once we reach below 5 nanometers, and they accumulate in kidneys. And that's when at this size actually is often used for diagnostic, for example, in medical diagnostic, because at this size they can be filtered by kidneys and eliminated from the organism. The same with shapes. Okay, laser pointer. The same with shapes. And for example, with coatings, negatively charged, neutral, and positively charged. Again, we see higher accumulation in response to positively charged in all organs. And this is example just with ceria oxide with one of model organism C. elegans. And ceria dioxide has 4 nanometers, so the same size and 4 different coatings. And indeed in C. elegans, the ceria dioxide that is coated positively charged coating is actually the one that results in the highest accumulation, and it doesn't matter with phytin here or without phytin nematodes. And if we look at the toxicity of those particles, again, positively charged particles are the ones that show the highest toxicity. While negatively and neutral charged particles actually don't show toxicity until we reach really, really high concentrations. So far we kind of consider size and solubility and shape, but what about surface chemistry? And with that, I just want you to also look at the poll question And the question is, what do you think happens to nanomaterials after they enter those environments, wastewater environment and soil environments? Do they stay unchanged? Do they dissolve? Will be their services modified due to formation of ecocorona, and whether it would be B and C, for example? Okay, I start seeing responses, and there are some responses says B, they can dissolve, and some responses that says B and C. And actually, if you look at the question, it's not specific nanomaterials, right? So if it is unstable like silver, it will dissolve. However, all nanomaterials also will be modified due to formation of ecocorona. So the answer both B and C would be correct, depends on the particles. And what do I mean by modified? So I'm talking here about environmental transformation. Why is it important? Because when particles as synthesize, we have one particle, right, with certain coatings, they release in the environment. And for example, in this case, we continue with silver, the same image that you saw before, but now I want you to look at the right part of the image. And now we have silver in wastewater. And it is environment where it has high concentration of sulfur. When you have high concentration of sulfur, the particles eventually will be sulfidized. And the whole thing will be converted in sulfidized silver nanoparticles. Once they converted in sulfidized silver nanoparticles, then their dissolution will change, it will significantly decrease, and also it will change their bioavailability and toxicity. And this is just example, for example, how toxicity changes, again, in the nematodes, the organisms that I frequently work with. And if you look here, this is in response, that measure is reproduction, number of offspring per adult. And here we have response to ions at this concentration, then response to silver nanoparticles as synthesized. They're less toxic than ions, and those silver nanoparticles are sulfidized after they're being released into the environment, right? So they went through environmental transformation, toxicity is decreased significantly. However, if you remember in the poll question, the answer was that they will be modified due to formation of ecocorona. What do I mean by ecocorona? So that sulfidation is only one of the processes, one of the transformations that those nanoparticles can undergo to in the environment. There are also a lot of other transformations. And it depends, for example, if they are present in the solution and there is an effect of temperature, pH, salinity, that will also modify the surface chemistry of the particles. Another thing that we just looked at is sulfidation for silver nanoparticles. For example, if you have other particles, zinc oxides, they may be phosphorylated. Can we have dissolution, there is aggregation? This is all based on nanomaterial properties. And finally, we have such as biomolecular properties, meaning that we have presence of different metabolites, we have organisms that can excrete different proteins, there are lipids present, natural organic matters, all of it can actually be attracted to the surface of the particles and form so-called ecocorona. Again, when that ecocorona is formed, it will govern the bioavailability and toxicity of the nanoparticles. And this is just kind of to demonstrate that once nanoparticles are changed, go through environmental transformation, it changes in size, surface properties. There is change in how much metal, for example, metal ion being released, right? And change how much is being taken. Another thing, if they interact with pollutants, would they be carry pollutants to the organism too? So all of that results in changes in physicochemical properties and hence changes toxicity. So that gets much more complicated. So how do we really take into the account those potential risks when we design novel nanomaterials? And there is a huge demand of novel nanomaterials, right, for their amazing properties. Yes, in some cases we can control, for example, dissolution. Here is example how to decrease the amount of dissolved copper with copper oxide particles. They were doped with iron. That's one, for example, of the examples that people do to decrease dissolutions. There is obviously, we call it green nanoparticle synthesis, whereas the core of the particle use can be as safe, as biodegradable, and biocompatible as possible. We can also control shape, charge, and size to also diminish toxicity. And obviously, it's all start with the toxicity screening on in vitro and in vivo. And for example, if the nanomaterials being developed for pesticides delivery, right, against certain targeted organisms, it's very important to verify that there is no toxicity in non-targeted organisms. So what I want you to think about then, when there is actually production, design and production of novel nano-enabled products, right? There are different stages those products are undergo to, started with the concept development, then preliminary design, laboratory scale production, pilot production, and market entry. If you think about which stages do you think would be the most feasible to control at the safety of the developed nano product? I see different responses. There are majority that go into preliminary design and laboratory scale, and that would be the correct answer. We definitely do not want to control it at market entry because it's the last stage. But good job, guys. Some people said preliminary design, laboratory scale production, market entry. I put that in to kind of make it a little tricky because market entry is there. So if you looked at those stages right here, right, started with concept and ending with market entry, and this is your ability to influence safety of design, and this is cost to manage health and safety risk. And you can tell that as you move through those stages, it's much harder to influence the safety of design. And it will be much more expensive. It's pretty much impossible once the product is released to the market, because that's a lot of stages it went through and it's already in the product. So it's much easier, theoretically, to at least think about the safety and go through all the testing at preliminary design and lab production stage. However, what is also important, this is kind of another diagram that shows different factors affecting toxicity, because I a little bit simplified it in previous. We talk about size, shape, surface chemistry, transformations. What I didn't mention, there is also different dimensions to the materials. I mainly focus on, for example, zero-dimensional, right, and one-dimensional, but we also have two-dimensional nanomaterials, such as graphene oxide, nanosheets, which is atomic sheets exfoliated from the product, or we have phosphorine. Sometimes we have nanocomposites, which is called functionalized nanosheets. It can be silver deposited directly on those graphene oxide sheets. So all of that makes it really complicated to evaluate those potential risks if we need to consider everything, right? Material composition, dimensionality, concentration, and so on. So what is the best approach to really do it? So as I mentioned, we start with in vitro models and in vivo models, and eventually we get to in vivo mammalian models. If it's obviously drug for delivery, it will go through clinical studies, but that's not sufficient because all those data need to go into and be part of in silico models. And in silico models is actually modeling and predicting based on the changes in nanomaterials properties, and plus using the toxicity already data that are available, can we predict how those novel nanomaterials will be expressed in their toxicity, basically? Can we predict the risk? And therefore, in silico models are kind of fitting into experimental toxicology, and vice versa, experimental toxicology is fitting in computational toxicology. So to really help us, where do we start, right? There is actually already a lot of different databases available, and they're freely available. For example, if you want to look at toxicology of different engineered nanomaterials, you can use a nanomapper. Or if you want to look specifically for nanomaterials that are used in biomedicine, then it would be the database that is collect already the toxicity based on the properties and interactions is Nanolab. And another database that is specific for modeling and determining nanobiological activities, for example, interaction of nano with different proteins, right? And I also want to refer you to this paper Lee et al. In Nanomaterials in 2021. And he's discussing, I think there is at least 9 different databases that he's also discussing and providing examples. So with that, I would like to thank everyone. And if you have time for questions, please don't hesitate to ask.
Thanks, Olga and Paul. We have about 1 to 2 minutes left for questions. Would you like me to read you some from the Huva?
Well, I see chat too. Okay.
Yeah, I think the chat was just their answers from before. And one of them is, can nanotechnology be applied to foods?
Yes. Okay, it's very easy because first of all, the food is naturally nanostructured material, and actually this is the gray area in the regulation. Can you add material that are already exist in the food at nanoscale? So actually the food companies don't want to admit that they're working with nanomaterials. They classify it as submicron particles. But actually, if you take a look on the food structure under the SEM, just Google it, you'll be surprised how food looks at the nanoscale. But yes, one of the first nanotechnology patent was patent from the Mars chocolate company in, I believe, in early 80s, titanium dioxide coating to increase glassiness of the famous chocolate candies from Mars. Now we a little bit more picky about it, but yes, now we have conversion between food and medicine. From pharma standpoint, food it's just oral administration of different components. From food, actually, we take care about the preventive health and good health. But yes, we all like to be healthy, and we need a good formulation in terms of the emulsion, in terms of particle to deliver all healthy components.
Thank you. So it is 10:30. I'm sorry that we couldn't get to all the questions, but if you could answer them in Huva, I would really appreciate it. You just go on the Q&A portion and you can click on it and answer them there. So our next session, we will have to jump Zoom session. So I hope to see you all there for data visualization. Thank you so much, Paul and Olga. I really enjoyed this.
Thank you for organization and leading.
All right, thank you, Paul. Chelsea, I can stay a little bit to